Yeah, so this is joint work with Melchior Wirth from ISTA and Haonan Zhang from UC Irvine. So the main object of this talk will be a way to measure somehow how a Boolean function depends on each of its bits. And so this way is done with respect to the influence function. So given a Boolean function f on the Boolean cube of size n, the influence of bit j on the function f will be the probability that upon flipping the jth bit, the function will also change its value at the output, where the probability is taken with respect to input bit strings, which I will assume to be uniformly distributed here. Then given this sort of local influences, you can define a notion of a total influence, or what people also call sometimes the average sensitivity of the function, which is simply the sum of all the bits at the input of the influence of that bit on the function f. In this talk, I will also call the function balance if the average of the function is equal to 0. And you can find examples of Boolean functions just looking at voting systems. And so the idea here is that the smaller the influence of each of the individual bits, the better the voting system will be. So if you start with a dictatorship, for which the function takes the value of one of its bits with a certainty, then the influence of that bit, so the bit j, will be equal to 1, and the influence of any of the other bits will be equal to 0. So the total influence is equal to 1 here. If you move along the kind of voting systems you can find, you will end up with K-junta. So this is a French K-junta here, where the idea is that the function only depends on k of its bits. And so I take the set capital J here of those bits, and the influence of anything outside, any bit outside of this set will be equal to 0, and the influence of bits inside of this set will be essentially constant. So the total influence in this case will be of order the number of bits that the function depends on. So there's actually a reverse, converse result to this statement, namely that if a function has a small influence, then it will be somehow very close to a K-junta. So this is a result due to Friedgut. That's the first of the three protagonists of the talks, and I will explain later how you can extend this to the quantum case. Okay, so if we move along, you end up with the majority function, for which you can show that the influence of each individual bit is of order 1 over square root of n, so the total influence is of order square root of n. And you can achieve actually a better local influence than what the majority function gives you. So if you construct a function called the tribes function here, which I won't detail more than that, but the influence of individual bits for this function is of order log n over n. So the total influence is of order log n. And I can again ask the question, okay, can you achieve a better low bound than this low bound? And the answer to this question is no. So this is due to the so-called KKL theorem from Kahn, Kala, and Lineal, which states that any Boolean balanced function f has at least one of its bits that has influence at least log n over n. Okay, so these were classical concepts, which I will now try to extend to the quantum setting. So first, I will explain how you can extend the notion of Boolean functions and inferences to this quantum setting. In the second part of the talk, I will show you how one can low bound individual inferences and then recover some sort of quantum extension of the KKL theorem. In the third part of the talk, I will mention a quantum extension of Friedgut's theorem. And finally, I will explain how one can use Friedgut's theorem to get new learning algorithms for unitary matrices with small local inferences, total inferences. Okay. So let me start with a dictionary of concepts. On the left-hand side, you have classical objects, and on the right-hand side, you have quantum objects. And the idea is here that given the definition I gave you previously of the influence, this like probabilistic notion, and it's not so easy to see how you can extend this to the quantum case, but luckily for us, we have another way to write the influence classically, which only takes into account analytical objects. So for this, I first have to define the notion of a discrete derivative. So when you apply it to a function that can take actually real values here, it's just defined as the function minus the average of the function on the jth bit. So this can be easily extended to the quantum case. You just take the quantum derivative of a matrix A over a vector space of dimensions to the n to be A minus 1/2 of the partial trace corresponding to the qubit you're considering applied to this matrix A. Then, given the parameter p greater than or equal to 1, you can define the notion of an LP inference, that is simply the expected value of the p power of this discrete derivative corresponding to bit j on the function f. In the quantum case, this is easily extended by essentially replacing the average by weighted Schatten norms. So the quantum LP influence of my matrix A will simply be the pth norm of the normalized Schatten norm over the P of this quantum derivative. And again, simply as in the classical case, when I mentioned that balance functions are functions of average equal to 0, in the quantum case, they will just be traceless operators. Okay, so now a Boolean function is simply a function that takes values in -1, 1. And one way to extend this to the quantum case that would be simply to further impose that the operator only takes values -1, 1, eigenvalues -1, 1. And to do this, you just have to impose that it's self-adjoint and that it squares up to 1 to the identity matrix. Okay, so at this stage, you might think that all the concepts very easily extend from classical to quantum. There is one very big difference between these two settings, which is in what I said before, that these LP influences are somehow the same as the initial notion of influence in the classical case. This won't be the case anymore in the quantum case. So classically, the way to see this is simply because the value of discrete derivative on the function can be either -1, 0, 1, and you can easily see this, use this to show that for any parameter p greater than or equal to 1, the pth influence that I defined before is exactly corresponding to the first notion of influence I gave you before. In the quantum case, you can find very easy counterexamples to this. You can, even for 2 qubits, you can find a quantum Boolean function, so which satisfy these two identities for which the L1 influence and the L2 influence would be different from each other. So this is an observation that was already made in an original paper of Montanaro and Osborne, where they actually define this notion of quantum Boolean functions and already prove some results related to them. But this somehow also, this observation also tells us that if we want to extend any of those classical theorems to the quantum case, you will always have to necessarily say with respect to which parameter you're trying to prove your result. So which parameter p here. Okay, so let's see how it goes in the case of the KKL theorem. So this is the classical result, which says that for a balanced Boolean function f, there exists one bit whose influence is at least log n over n. And classically, you can prove this using another result, which is the third protagonist of the talk. That's Talagrand's inequality, which says that for any function f of the Boolean cube, here I assume that it's a balanced Boolean function, but you can actually have similar results for functions that take value in the reals. You can find a universal constant independent of the function, such that the L2 norm square of the function can be controlled by the sum of all the input bits of the ratio of the influence of that bit on the function divided by 1 minus the logarithm of this influence, essentially. So once you have this Talagrand inequality, it's just a one-line proof to show the KKL. The idea is to simply assume first that for all input bits, the influence of that bit is at most 1 over square root of n, because if you had one bit that had influence bigger than this, then you would be done. You would have proven the result. Then you use Talagrand's inequality. So on the left-hand side, you have, since we assume that the function was a balanced Boolean function, the 2 norm is actually equal to 1 here. Then you use Talagrand inequality. You get the sum over the bits of influence divided by this thing here. The denominator, you can lower bound it using this 1 over square root of n. And then this sum, you can simply upper bound it by the total number of bits, so n here, times the maximum influence. And so you see directly that the prefactor that you end up with is exactly what you wanted, so n over log n. So you can just put this on the other side of the inequality, and you will have proven the KKL result from Talagrand. So from here, the path from classical to quantum is quite straightforward. So first, we will show that one can recover Talagrand inequality for quantum Boolean functions. And then we'll use exactly the same trick as before to get a quantum KKL. So here's one version of our Talagrand inequality. And so on the right-hand side, we only have quantities which depend on the L1 influence. So we find essentially, again, like universal constants, positive constant C, for which this inequality holds for any matrix A, traceless matrix A, whose infinite norm or operator norm is bounded by 1. And I won't have time to explain the details of the proof, but maybe one observation here, one remark is that the proof techniques we use are quite robust, so they actually extend to qubits, but also to constant variable systems. And I think it would be interesting to see what this kind of inequalities actually tell us about the physics of those constant variable systems. But okay, so once you have this L1 Talagrand, you can directly prove L1 KKL. So we know that now that for any quantum balanced Boolean function, there exists an inferential qubit in the sense of L1 inference. And we can actually extend this to any LP inferences for P strictly less than 2. So we just have to show, again, a Talagrand inequality for that LP inference, and that would give us directly a KKL theorem for that LP inference. However, the constant C here will then depend on this parameter P. So when P goes to 2, it turns out that this constant C actually diverges. So we cannot show KKL yet for the L2 inference. And this was actually the original conjecture of Montanaro and Osborne. This is still open at this stage. Okay, so let me move to the second main result of our paper, which is an extension of Friedgut-Runta theorem. I'll remind you of the classical result. So given a Boolean function f and some approximation parameter epsilon, there will exist a K-Runta, so a function that only depends on k of its variables, such that f is epsilon close to g in L2 norm, as long as you can take k to be exponentially depending on the influence of the initial function f divided by the approximation parameter squared. So to extend this to the quantum case, first I have to explain what a K-Runta is in the quantum case. This is simply going to be a matrix which only is supported on k of its qubits. So on the set J here, which is of size less than k. And given this definition, our quantum Friedgut-Runta theorem looks like this. So we have that for any matrix A over n qubits, there exists, and for any approximation parameter epsilon, there exists some matrix B, which is only supported on k qubits, so K-Runta, such that A is epsilon close to B in Shetland 2 norm, as long as you can take k to depend on A in the following manner. So it will depend on the L2 norm of A, on the L1 and L2 inference of A, and exponentially on the L2 inference of A divided by the approximation parameter squared. So maybe two remarks. Again, this extends to continuous variable systems. So this is, again, because we are using quite robust functional analytical results for the proof. And second remark is that we actually do also recover the classical results here. So the way to see this is that if you take A to be a classical Boolean function, then the 2 norm would be equal to 1. As I mentioned before, all these LP inferences actually coincide with each other. And so this prefactor only becomes the inference of A, and this exponential term is the same as the one we had here. Because it's actually really a truly quantum generalization of the previous result. So in the remaining part of the talk, I want to explain how one can now use this quantum Friedgut theorem to devise efficient learning algorithms. And I would like to first start with the classical setting. So classically, the idea here is that you are given a black box access to some Boolean function f, and you want to know how many times you have to query this function so that you can learn some description of an approximation f tilde of f. And of course, this will depend very much on what kind of function you have at hand. So this is the notion of concept class. Which kind of set of functions does this function belong to? And what is your query model? So can you query the function on a bit string that you have chosen, or do you only have access to random examples? And there are many results in this direction. I just want to point one of them from the 2007 by Haonan and Servedio. And what the idea is that they could show that for monotone Boolean functions, the inference of that function can be upper bounded in terms of some other measure of complexity of the function, so namely the square root of the logarithm of the partition size of the function. So you can think of this as simply the minimal way you can divide your cube into subcubes where the function will be constant. And they use this together with this classical Friedgut-Runta theorem to show that there will exist a learning algorithm for those monotone Boolean functions which outputs L2 approximation with high probability, given random access to the function in times that scale both polynomially in the number of bits at the input and polynomially with this partition size of the function. So since this is polynomial in P of f, this is somehow telling you that P of f is a good complexity measure for learning such functions. And as I said, like the proof really uses this classical Friedgut theorem. So the idea is quite simple now. We just want to find a quantum extension of this. using our quantum Friedgut. And in the quantum setting, now we are given black box access to a non-unitary U. And the question is as before, so how many times do we have to query this unitary so that we can learn some classical description of the unitary given, description of a good approximation of this unitary. So the approximation I would call U tilde here, and with high probability. Again, it depends on where the unitary lives and how do you actually query that unitary. So you can think, for example, of just querying the unitary on the states that you choose, then maybe entangled states, and so this would be just like essentially you can in the case where you query U, you can assume that you have access to the Choi matrix, or you query something a bit stronger, you can query control unitary, control U. Okay, so in this table, I essentially summarized our result. The first line is just a restatement of the previous one, where I just restate the result only in terms of the inference. So this result of Haonan and Rouzé is like if the inference squared is of order log n, and given access to random examples, then the complexity for learning this function is poly n. Our result could be understood as a quantum extension in the sense that if you know that the square of the L2 inference plus the L2 inference times the log of the L1 inference divided by log n is a constant, and if you are given access to control unitaries, then you can find an algorithm that that outputs a good approximation in sample complexity poly n. I also want to point at another result which will be described tomorrow, which is in the setting where U is already known to be a K-junta. So we don't know where the junta acts, but we know that the unitary only acts on K qubits. And in this paper, having access to the Choi matrix of U, it was shown that you can actually get a query complexity that only scales with K, so independent of N. It's quite a strong result. So the talk will be tomorrow. I also want to point out the fact that so the next talk today will also be somehow related to what I'm talking about here, but there the measure of complexity that will be chosen is the degree of your process instead of the inference. So there are, of course, relations between those things. So this is actually the main result in its full glory. So we show that given oracle access to control unitary and for any approximation parameter epsilon and probability of failure delta, there exists a quantum algorithm which outputs with probability 1 minus delta the Pauli coefficients of a good approximation, U tilde of U, approximation L2, as long as you have access to that many queries of U, of control U. So you see directly that since this is polynomial in the exponential of those inferences, if you impose this relation on the L1 and L2 inference, you recover a poly n sample complexity. So the idea is, as already said, so we use quantum Friedgut theorem to say that we will be close to a K-junta, and then we just have to learn where the large size Pauli coefficients are. So for this, we use already known results by Montanaro and Osborne, and then we just use an algorithm to learn those the corresponding Fourier coefficients. I think I'm running out of time, so I will stop here, and thank you for your attention. Yeah. I think there's.
Can you maybe go back to this quantum KK theorem?
Mm-hmm.
Is there maybe an intuitive explanation of this? So, I mean, what are the conditions on an observable, like such that I can just kind of replace it with like a local observable, like in intuitive terms?
So you would want F to be a local? No.
I mean the quantum case.
Oh, sorry. Here you mean, right?
No, not like I mean, you had this one where you said the observable is close to local observable. Or maybe it was not the KKL.
The Friedgut, you mean? Sorry.
Sorry.
Yes. No worries.
Yes. And can you intuitively explain what this condition on A means that is term on the right hand side is small?
The condition on A, I mean, we have no conditions on A, right? It's
well, let's say, I mean, this is only this inference more, but can I somehow intuitively calculate this?
I mean, essentially, yeah, it's somehow, says, oh, yes, sorry. So you were asking what is this condition on the inference of A for which we know that you have a good K-junta approximation to it. In a way, this is measuring the smoothness of these observables. So classically, it would be just looking at the sum of the partial derivatives of the function. So if the function has very small partial derivatives on many of its inputs, then you know that it is essentially the value of the function will be dictated by the inputs for which this gradient is large, right? So this is somehow mimicking this idea here.
Other questions?
I can, in the case of, so what's the semi-group underlying structure? If second question is the proof different from the classical one in line, and what is the semi-group if you want to talk about it in the case of CV systems? So.
Very good question. So the semigroup would be what you would expect. So it's just the depolarizing semigroup, tensor product depolarizing semigroups in this case. It's very nicely actually, we can follow the classical proof up to the very last line, and then we have to do something else. Classically, the fact that all these influences are the same is quite nice. You can just stop at some point here. We have to go one step beyond and use Holder inequality at some point which is the reason why we're getting these two inferences here, but most of the classical proof actually extends nicely. And so the other question was, what do we choose here for consumable systems? Then you can just use a quantum extension of the Ocean-Uhlenbeck semigroup, as you would expect. And of course, the L2 norm would be replaced by this weighted L2 norm with respect to some Gaussian state. But the proof extends because we also have hyperconductivity for that Ocean-Uhlenbeck semigroup, so everything goes through, essentially.
In the spirit of the previous talk, so you're counting how often do you then measure over multiple copies of the outputs that you get out, or do you measure single copies?
I'm measuring single copies here. Yes. Yes.
How tight are them? Like, so you're using influence to bound the learnability.
Yeah. It's also a very good question. So if you actually had access to more than just knowing that these inferences are small, say that if you had access to the degree of the Boolean function, then you could do much better in the sense that you would get a bound that is polynomial in 1 over epsilon, not exponential here. So it very much depends on what you have access to here. And if you only know the inference, I think you cannot improve this result. But if you know that there is a degree bound, then you can do much better. Yeah. And I guess we'll see this in the next talk also.
Okay, if there are no other questions, let's thank the speaker.